Okay. Okay, so welcome to the Zoom seminar. So today's speaker is Shuntaro Tsubouchi. I think you missed the I.
Oh, that's oh,
Anyway, so he is a student of University of Tokyo and get a PhD this September. So in 1 month later. And the title of his talk is Continuity of a Spatial Derivative for Perturbed Singular Equations. Okay, please, Shuntaro,
thank
start.
you for your kind introduction. I am Shuntaro Tsubouchi at University of Tokyo. I'd like to thank Professor Mitake for giving me a nice opportunity to talk about my recent research. Now, let's start. Uh, in this talk, we treat these one Laplace elliptic or parabolic equations perturbed by P Laplacian. The main purpose is to briefly explain how to prove continuity of a gradient described as at the bottom of the slide. So more precisely, we consider weak solutions in the distributional sense, and we aim to prove that the spatial gradient, which is assumed to be in LP, admits local C0 regularity. Here, the right-hand side f is a given function, and it is assumed to be in a suitable Lebesgue space LQ. There are two mentions. First, I like to note that for the elliptic case E, the vector valued problems can also be discussed. But in this talk, I omit the details. So we mainly discuss scalar valued problems. Secondly, for the parabolic case, we have to let the exponent p be greater than 2n over n plus 2. This assumption is typical when we consider boundedness of a spatial gradient. In the next slide, I briefly explain some mathematical models or elliptic equations as well as an elliptic system is derived from the following Euler-Lagrange problem. Here, the corresponding energy functional contains a sum of the total variation energy and the p-Dirichlet energy. This type of energy functional can be often appears in the fields of fluid mechanics and material sciences. A typical example is Bingham fluids, including oil, toothpaste, and various fluids that contains both plasticity and viscosity. These plasticity and viscosity effects herein respectively correspond to one Laplace and two Laplace operators. So more precisely, in this model, you denote the three-dimensional velocity of a Bingham fluid. So when this velocity is very sufficiently small, then some conventional effect can be abundant, and therefore this vector field U satisfies some second-order elliptic problems of Stokes. So this vector field will satisfy some second-order elliptic Stokes problems. Here f corresponds to f becomes a slope of a scalar valued pressure function. So it is important to consider some vector valued problems, but when we consider a unidirectional Bingham fluid flow in a pipe cylinder, like this figure, then the corresponding Stokes problem becomes or elliptic equation, this one, or elliptic equation with p equals 2. And moreover, the right-hand side f becomes constant. Another example is found in crystal surface growth under roughening temperatures, modeled by Chupon in 1993. There, the crystal surface energy is considered with P equals 3. And here, the scalar function U denotes the height function of the crystal. And F correspond to some chemical potential. The resulting equations for for U itself becomes the fourth order parabolic equations or scalar valued parabolic equations. But in the stationary case, this height function U must satisfy the second order elliptic equation. So this one with P replaced by 3 and moreover F becomes some sufficiently smooth functions. So for these on mathematical formulations of these models, please find these references Duvall Lyon's classical textbook in the 1970s and a paper given by Schipon in 1993 and some monograph given by some paper by Kohn in 2012. Anyway, so we next mention some optimal regularity for stationary problems. For the elliptic equations, its gradient is expected to be at most Hilda continuous. More precisely, for the given energy density E, its convex French dual E star generally becomes a solution. Here the energy force term becomes minus n. So it is the constant. So therefore, the convex dual function often gives some possible regularity of weak solutions. In a problem, the facial dual of the energy density is given by this one. So this function is in C1 alpha with alpha given by this. Anyway, so it is possible to expect some C1 alpha regularity of this weak solution. However, this C1 alpha conjecture is very difficult and it has not been answered affirmatively. However, my recent works established at least continuity of a gradient. So in other words, C1 regularity, at least C1 regularity is true. This is what I'd like to tell in my talk. In this slide, I briefly mention P-Laplace regularity results for elliptic and parabolic problems. If we remove the one Laplace operator and consider some P-Laplace problems, then it is well known that the spatial gradient is continuous. Moreover, it is always Hilda continuous. In this sense, P-Laplacian keeps continuity of a gradient. I have listed a few fundamental works in this slide, and there are many excellent experts who established P-Laplace regularity theories. Although Hilda gradient continuity for P-Laplace type problems has been well established. When P equals 1, it is no longer possible to obtain continuity of a gradient. So in fact, even in the simplest one-dimensional case, any absolutely continuous function, scalar valued function, will be one harmonic as long as it is non-decreasing or non-increasing. In particular, this type of piecewise linear function becomes a solution, and therefore C1 alpha is less hopeful, even for simple this one Laplace equation. In this sense, the one Laplace operator breaks continuity of a gradient. Such a problem is basically because the diffusivity of the one Laplace operator is anisotropic, while that of P, while the diffusivity of delta P Laplacian is isotropic. This will be explained later by giving some explicit computations. However, when it comes to at least continuity of a gradient for one P Laplace type problem, P Laplacian will defeat one Laplacian. This is what I'd like to explain in my talk. So my talk consists of two results, which deal with interior C0 regularity of a special gradient. For elliptic regularity, both the scalar case and the vector case are treated in two papers. A parabolic regularity result has also been shown in my recent preprint, which only deals with the scalar case. Parabolic systems problems in my preparation, but so anyway, I'd like to discuss the scalar case only. Before establishing these caesal continuity results, these caesal regularity of a gradient, some gradient continuity was already proved by Professor Giga and myself in a special case where a solution is a scalar, when a solution is both scalar valued and convex. The methods therein are heavily based on convex analysis and the strong maximum principle. So in particular, a gradient is treated not only as a distribution, but also as a subgradient of a convex solution. But in analysis in talk, in this talk, or analysis removes this convexity assumption, and moreover, this will work even for vector value problems and moreover parabolic equations. So I'd like to talk about these two results. The contents of this talk are as follows. In the first section, we first explain what is the main difficulty of our elliptic and parabolic equations. Also, it will be demonstrated how and why gradient continuity can be shown. The basic strategy itself is found in recent research on a certain very degenerate elliptic problem. We will also compare our very singular problems with the very degenerate ones. In the remaining two sections, I'd like to briefly explain the outlines for each equation, each elliptic and parabolic equation. So this is the end of the introduction, and now let's move on to section 1. To explain our main difficulty, we set a real-valued convex function ES for a finite number S. Then our elliptic equation can be written by this form. Here, and the sum of the energy density E is the sum of E1 and EP. Formally differentiate these equations by the spatial variable xi, then we can notice that the Hessian matrix nabla square E nabla U appears. We can notice this equation. The main difficulty is that this quiescent matrix is no longer uniformly elliptic in a suitable sense. So roughly speaking, we will face a problem that this equation is no longer uniformly elliptic. So this uniform ellipticity is not in the classical sense, but it does make sense by giving some computations. This uniform ellipticity can be measured by considering a certain ratio of eigenvalues, which is often called ellipticity ratio. Anyway, it will be difficult to prove header continuity of the gradient of the partial derivative because this Hessian matrix is not uniformly elliptic. Similarly, even for parabolic equations, our problem will become no longer uniformly parabolic. So continuity of a spatial gradient will be very difficult. So we have to see some we have to compute some eigenvalues, and we compute the Hessian matrix of this ES, and this Hessian matrix is given by this form, given by this, as long as the point is non-zero, this term makes sense. So anyway, this eigenvalues and eigenspaces of the Hessian matrix are given as follows, and we should note that when S equals 1, this S minus 1 Z0, the norm of Z0 followed by S minus 2. When S equals 1, the eigenvalues above becomes always 0. This becomes 0. Even when the point Z0 is non-zero. So in other words, this means that even when the gradient does not vanish, the one Laplace operator becomes always degenerate elliptic in a direction of a gradient. So such property is substantially different from the P Laplacian. Also, we should note that ellipticity of delta 1 in other direction never degenerates, and even worse, this will blow up as the gradient degenerates. In other words, the one Laplace operator contains both degenerate and singular ellipticity. Such anisotropic diffusivity of one Laplacian will be very difficult to handle in the existing regularity theories, including the de Giorgi-Nashimoto theory or the Schauder theory. Now, we calculate the Hessian matrix of E similarly, and for this Hessian matrix, we can consider a ratio, so-called the ellipticity ratio or parabolicity ratio of the Hessian matrix. This is defined by the ratio of the largest and lowest eigenvalues. The computation result here so this term implies that or difficulty appears as the gradient vanishes. More precisely, since the exponent 1 minus p is clearly negative, and therefore this ratio will blow up as the gradient vanishes. Such behavior of this ratio implies that all elliptic problem will be no longer uniformly elliptic near the facet. The facet a place where a gradient vanishes. Some of you may recall so-called PQ growth problems, but please be notified that this is basically different from PQ growth problems. So in our problem, non-uniform elliptic structures will appear as a gradient vanishes. But for PQ growth problems, some non-uniform elliptic structures will appear as a gradient blows up, not as a gradient vanishes. Also, it should be mentioned that when B equals 1, so the one Laplace term, so when the one Laplace term is removed, then this ellipticity ratio is clearly everywhere bounded, and in particular, here the continuity of this of a gradient will be expectable for one Laplace problems. So the main difficulty is the coefficient matrix nabla square E nabla U becomes no longer uniformly elliptic or no longer uniformly parabolic near facet. So this prevents us from using standard tools in the De Giorgi-Nishimoto theory to prove header continuity of a spatial derivative. In particular, it is difficult to give quantitative gradient growth estimates across a facet. Also, another problem related to Sobolev interior Sobolev regularity will arise. Precisely speaking, we want to treat these equations in the sense of W minus 1, 2 or L2 W minus 1, 2. But if we to verify this, we have to check this L2 regularity. So in particular, the solution, we have to verify second order Sobolev regularity by appealing to some difference quotient methods. But these difference quotient methods will substantially rely on some uniform elliptic structure or uniform parabolic structures. But in our problems, they are not such a good property because all problems becomes no longer uniformly elliptic or parabolic near the facet. So it seems less easy to verify this L2 regularity. This problem is basically due to non-uniform elliptic or parabolic structures of this term. So we have to relax such a bad operator by another well-behaving one, which can be given by some relaxation. So in other words, we have to relax the density E by some sufficiently smooth E epsilon, such that the corresponding ellipticity or parabolicity ratio is everywhere bounded, depending on the approximation parameter epsilon. So we have to appeal to some approximations. In the previous slides, we have observed that our main difficulty will appear in a facet, of the solutions. But there is some hope for gradient continuity because as long as the gradient never vanishes, these equations can be said to be uniform elliptic or uniform parabolic as long as the gradient never vanishes. So we'd like to introduce some truncated gradient, this G delta nabla U, and the main purpose of this talk is to prove header continuity of this truncated gradient. Here I have to emphasize that this truncated gradient is supported in a place where a gradient never vanishes, and therefore, in such a place, this equation becomes uniformly elliptic or uniformly parabolic. So it is possible to expect header continuity of a gradient, but these header estimates substantially depends on the truncation parameter delta. So when we let delta to 0, or header estimates will blow up, and therefore it is no longer possible. It is less hopeful to get gradient continuity across gradient gradient growth, some growth estimates across a facet. But still yet, it is possible to conclude continuity of a gradient because this truncated gradient converges to non-truncated gradient uniformly. So this uniform convergence is very important. In particular, continuity of this truncated gradient for each fixed delta implies continuity of non-truncated gradient. That is the key point. So, but so this type of strategy is found in very degenerate elliptic problems, and this will be explained. This is explained in the next slides, in the next 3 slides. So the very degenerate elliptic problems, which could be a counterpart of very singular equations, is given as follows. The main difference is that the energy density E is replaced by the convex dual function E star, the facial dual of or energy density. This equation is concerned in an energy minimizing problem given by this right-hand side. This problem is originally derived from congested tropic dynamics, which was first modeled by Carrier, Jimenez, and Sant'Ambrosio in 2008. Here, it should be noted that the totally the same energy density function E is considered, although some detailed setting might be different from ours. An important fact herein is that the optimal tropic flow, so the minimizer of this energy function is given by the term uniquely given by the term nabla E star nabla V. Here the function V solves this very degenerate elliptic equation under Neumann boundary condition. This fact is shown by duality arguments shown by Brasco, Carrier, and Sant'Ambrosio. After the unique existence of the minimizer is shown. So it will be natural to consider some continuity of this minimizer. Surprisingly, continuity of this minimizer is well known, at least for C0 regularity. The well-known fact therein is that for each truncation parameter, for each fixed truncation parameter delta, the truncated gradient B plus delta nabla V. This is defined similarly to ours. So the truncation parameter is replaced by the truncation parameter delta is replaced by B plus delta. So this truncated gradient is continuous. So in particular, the uniform limit with respect to delta. So this vector field is also continuous, and therefore the minimizer itself is also continuous. Proofs of this theorem are found in the following three papers. The first by Sant'Ambrosio and Vespucci deals with the special case when the space dimension is 2. And the second by Colombo and Figari generalize the space dimension n and the convex density function E star for scalar problems. The third by Bogarin, Dussal, Jova, and Passarelli di Napoli was recently published, and this discusses vector-valued problems. Our proof of a priori estimates is highly inspired by this third work, and we appeal to standard methods, including de Jory's truncations and freezing coefficient methods. So please be notified that continuity of this optimal traffic flow for the degenerate problem seems to be similar to ours or our continuity result on the spatial gradient nabla U, because the same energy density E is treated. So we will treat the same energy density, and it might be expectable to show continuity of a minimizer, minimize the spatial gradient. Continuity of a spatial gradient will be expectable. So I'd like to make some comparisons between my very singular and degenerate problems. The right-hand side is a very degenerate problem, where the energy density is a convex dual of function of our energy density. Here, it should be emphasized that the dual density E star also has a non-uniform elliptic structure in the sense that the ellipticity ratio, the corresponding ellipticity ratio will blow up near the degenerate region of the energy density. So near this flat space, this equation will become no longer uniformly elliptic. However, it is possible to show continuity of this truncated gradient. So when I happen to see this regularity result, I came to think that these problems might be seems to be like siblings, and therefore although of course their diffusion structures are totally different, but it might be expectable to get some similar regularity result. So the non-truncated gradient will be continuous. This is what I'd like to. So this result appears to be a counterpart of some continuity results in the very degenerate problem. So this is the end of the first section, and next let's move on to elliptic cases. The elliptic regularity result is as follows. More precisely, when the external force term F is assumed to be in LQ with Q greater than the space dimension N, then the weak solution is always in C1. The condition of Q is optimal when we consider C1 regularity of weak solutions to for example, classical Poisson equations. Although it's possible to discuss general equations or even vector valued systems, but for simplicity, we consider the typical 1P Poisson equation. Next, we give the definition of weak solutions to elliptic equations in the distributional sense. The main point is that over a facet, the term nabla U over the norm of nabla U does not make sense in the classical sense because the norm function is not differentiable at the origin. So therefore we should treat the one Laplace term as in the sense of a subgradient or a subdifferential. In particular, we will regard the term nabla delta 1 U as a divergence of L infinity vector field Z such that the following subgradient property is satisfied. The subdifferential set of the norm function is given as follows. So this vector field Z always in this set. Of course, there might be some possibility of generalizing the absolute value of the norm function. And in fact, at least I have succeeded in considering positively one homogeneous density functions. This will be explained later. As mentioned before, we should consider an approximation problem. And so this is substantial basically because some interior Sobolev regularity can be improved in some approximation problems. In particular, the very singular operator should be relaxed by this LBP epsilon. So the energy density E should be relaxed by E epsilon given by the convolution with the standard Friedrichs modifier. So for each fixed epsilon, we consider the unique weak solution of this relaxed equation under the Dirichlet boundary condition. This solution uniquely exists thanks to general theories from calculus of variations. Here the energy here's external force term F is also relaxed by F epsilon. For convergence of this F epsilon, we only require weak star convergence in LQ. So in particular, we may assume that this F epsilon is sufficiently smooth. Under these settings, strong W1P convergence holds. The proof of strong convergence can be accomplished by testing the difference function into this approximation equation. Such a good W1P strong convergence result itself is owing to the strong monotonicity of delta P Laplacian, while the one Laplace operator gives no quantitative monotonicity estimates. So maybe you feel that approximation is just approximation, but this good convergence itself follows from good property of the P Laplacian. Thanks to this strong convergence, W1P strong convergence, or C1 regularity problem boils down to some a priori estimates for approximating solutions. A merit of this relaxation is that this relaxed operator is uniformly elliptic in the sense that the corresponding ellipticity ratio of the Hessian matrix is everywhere bounded. More precisely, singularity of the non-approximated equation is given. Ellipticity ratio is given as follows for non-approximated equation. So this term is very singular, but this singularity can be relaxed by another V epsilon, by another modulus V epsilon. And because this V epsilon is far from zero, it is possible to get everywhere boundedness of ellipticity ratio. So we have replaced the modulus nabla u, the norm of nabla u, by this V epsilon. So corresponding to this replacement, we have to appeal to different truncation. So thanks to approximation arguments, our problem is reduced to a priori header estimates for approximation equations. Before giving the key header estimate, we should note three remarks. The first is that for this U epsilon admits local W22 and local W1 infinity regularity because the regularized operator is non-degenerate and moreover uniformly elliptic, everywhere uniformly elliptic. Moreover, when f epsilon is sufficiently smooth, it is possible to prove smoothness of u epsilon. So anyway, in particular, we may let u epsilon satisfy this equation in the sense of w minus 1, 2 locally. The second is that we are able to get local Lipschitz bounds independent of epsilon. The main point is to construct a test function whose support never intersects with facets of approximated solutions. For the scalar case, Mozart's iteration works, and even for the vector-valued system case, Desjardins truncation is very useful. Finally, the third is that we should adopt another relaxed modulus V epsilon. And as long as V epsilon is non-degenerate, as long as V epsilon bounded from above and the below, then it is possible to show continuity of this truncated gradient. So please be notified that we did choose another truncation with respect to V epsilon. And this is basically because the principal part itself is relaxed. So now we state the local a priori header bounds, which may depend on the truncation parameter delta, but this is independent of the approximation parameter epsilon. I mentioned again, wait. I'd like to mention that local header estimate, this local header estimates of this truncated gradient is very important in applying the Altsela-Ascoli theorem to this truncated gradient. Well, anyway, it is important to get header bounds independent of epsilon. So we briefly give a sketch of a priori header estimates. The main aim is to prove that the average limit always exists, and this limit also satisfies the Campanat type gross estimate. It is possible to prove this gross estimate by appealing to some basic analysis, including Desjardins truncation and some perturbation math arguments. But all analysis depends on whether a modulus V epsilon is not degenerate or non-degenerate or degenerate. If it is degenerate, if V epsilon may degenerate, we should appeal to Desjardins truncation. In particular, we consider this truncated function. We consider this truncated function, and a key point is that this function is a subsolution to a uniformly elliptic equations. Because this is possible because this function is truncated. And this function is suitably truncated, and therefore this is a subsolution to a uniformly elliptic equation. So some oscillation lemma will be expectable even when V epsilon may degenerate. Otherwise, we will verify that the average of a gradient never vanishes, and from this we appeal to some comparison arguments with harmonic functions. So such divisions can be done by measuring super-level sets of this V epsilon in a fixed ball PR. This type of strategy can be found in Manfredi's PhD thesis or Di Benedetto's paper in for P-Laplace regularity theories, including P harmonic flows and P-Laplace elliptic problems. But in addition, we should impose some technical assumption related to gradient bounds, but this will be explained later in parabolic equations. So the proof of gradient continuity is accomplished by some good convergence results. So we first let the approximation parameter epsilon to 0. Then, thanks to a priori header estimates, we are allowed to apply Altair-Ascoli theorem to truncate gradients, and in particular, up to a subsequence. It's possible we may assume that this truncated gradient uniformly converges to some continuous mapping V2 delta. On the other hand, we have already known that the gradient of approximation solutions almost everywhere converges to nabla U up to a subsequence because W1P strong convergence is already shown. Therefore, it is possible, thanks to this almost everywhere convergence, truncated gradients almost everywhere converges to G2 delta W. And therefore, these two limits must coincide with each other, and therefore, this truncated gradient should be continuous, must be continuous. Finally, letting delta 2 0, it is possible to get C0 regularity of a spatial gradient. So we have used two good convergence of solutions, and this can be verified thanks to by some monotonicity or ellipticity, good ellipticity or good monotonicity of the P-Laplace operator. And this basic strategy will work even for parabolic equations, as well as as long as these two good convergences are verified. So also in parabolic problems, we will have to verify these two convergences, these two good convergences. The generalizations of the stationary 1P Poisson problems can be done, but it will differ as long when it is scalar valued or vector valued. Briefly, I'd like to mention some generalizations. In the scalar case, we can generalize both 1 Laplace and P-Laplace operators. In particular, the total variation energy can be extended to a positively one homogeneous energy. So this satisfies the following identity. Under this setting, the approximation based on the Friedrichs modifier will works, and so it is possible to consider some generalized 1P Finsler Laplace operator. But in the system case, the density E is required to be somewhat symmetric. This is often called the Ahrenbeck structure. It is well known that without such symmetry, everywhere regularity of weak solutions is in general impossible. And therefore, the 1 Laplace operator cannot be generalized. For the system case, the regularization of the energy density is given by this straightforward relaxation. In particular, the 1 Laplace operator is relaxed by some sort of minimal surface operator. Although the approximation scheme is a little bit different, but our basic strategy, so this one, itself works even for system problems. So this is the end of parabolic regularity, and the final section we mentioned. I'd like to talk about the final section briefly, quickly. So the parabolic regularity result is given as follows. The unknown function u is assumed to be in the Bohner space LP W1P, and its time derivative is in LP prime W minus 1P prime. Also, so in particular, or equation is treated in the LP prime W minus 1P prime framework. So this function space is denoted by XP, and the external force term F is assumed to be in LQ. I have to mention some conditions on the exponent P and Q. We assume that they satisfy those three conditions. These three conditions, among them, the last one is a technical assumption, while the remaining two assumptions are very typical when we consider gradient continuity for parabolic P-Poisson equations. Please be notified that this condition gives no restrictions when P equals or exceeds 2. So in particular, there is some possibility of applying or regularity result to some Bingham fluid problem because in that problem P equals 2. So under these settings, a spatial gradient of weak solution is always continuous. This is the main result in parabolic equation. So similarly to the function xp, we introduce another function space xp0. This describes the class of test function. A weak solution for parabolic equation is defined as follows. So the main difference is that the test function is in x0p, whose time boundary, so the test function is assumed to be in x0p, and the time derivatives integrals with respect to time derivatives is treated by the pairing between W minus 1P prime and W1P0. Also, for parabolic problems, it will be a non-trivial question whether a weak solution can be constructed, because for the classical Fired-Galerkin methods, it is required that the energy density admits at least C1 regularity. But in a problem, this energy density is no longer C1 at the origin. So we have to appeal to some approximation of the energy density. We also mention some settings on P and Q because we have let P greater than 2n over n plus 2. We can apply Lyon's Martinez lemma and Oban Lyon's lemma. Moreover, so these inclusions and compact embeddings, this compact embedding are useful. So also this restriction enables us to appeal to existing theory for P-Poisson type harmonic harmonic flows. But this existing theory is shown by Lyon's monograph or Showalter's monograph. So in the proof of existing theory, this inclusion and this continuous compact embeddings, are used. Also, the condition Q, that Q is greater than n plus 2, and the technical assumption enables us to use continuous embedding. So LQ space can be continuously embedded into LP prime W minus 1P prime. So this technical assumption is is substantially basically because this equation is treated in the sense of LP prime W minus 1P prime. So So similarly, we consider an approximation problem by relaxing the energy density. So we relax the energy density by the convolution, and we consider the parabolic solutions to some under some Dirichlet energy, under some Dirichlet boundary condition, and we consider a unique solution of this equation. The unique existence itself follows from theory from classical theories by J.L. Lyons and Showalter. So similarly, we will verify that good convergence of a weak solution. In particular, we will verify that a solution strongly converges in LPW1P, local in time. This can be verified by testing the difference function multiplied some time multiplied by some time functions multiplied by this theta. So some multiplied function is tested. To verify this choice of test function itself is found in Cusi and Minjione's work, which deals with approximations for p-harmonic flows. But in our proof, we have to verify some good continuous or compact embeddings because the energy density is not smooth. So thanks to by making use of these good continuous these embeddings, it's possible to verify good convergence of weak solutions. And thanks to this convergence, we have to consider some a priori estimates for relaxed equations. So for the parabolic problem, we have to require that P is greater than 2n over n plus 2. This assumption is used in the proof of L infinity LP estimates. So gradient bounds of local gradient bounds. In the proof of local gradient bounds, this assumption is required. So anyway, it is possible to verify. It is possible to use in the classical sense. It's possible to treat this equation in the classical sense. So similarly to elliptic case, we may regard this equation as this equation as a uniformly parabolic as long as V epsilon is never degenerate. V epsilon never degenerates. However, a key point is used, but a key point is that a gradient never vanishes. So some gradient parameter mu, some parameter, this mu denoting the bound of gradients should be, we only consider the case this mu is greater than delta. This assumption is roughly speaking we consider only in some non-degenerate case. Anyway, similarly to elliptic case, it's possible to get header continuity for parabolic case, header continuity of a truncated gradient or parabolic case with respect to the standard parabolic distance. In our proof of a priori header estimates, this technical assumption is not used at all. The proof itself is very similar to elliptic case, but some technical assumption is also used. But the basic strategy is the same, almost the same with elliptic case. A significant difference is that
Shuntaro, maybe yeah, your time is
okay. Sorry.
Can you quickly conclude?
Okay. Yeah. I should hurry up. Okay, sorry. So it's possible to get parabolic estimates. Finally, some future works for anisotropic problems. I was inspired by some results in very degenerate problems, and inspired by by the work by Bogeran et al. I have succeeded in gradient continuity for elliptic problems and even for parabolic problems. For parabolic, for degenerate parabolic problems or some or partial regularity problems, less is known. This is still known. So there will be some future work, and it will be possible to expect this kind of regularity. So this is the end of my talk. Thank you for your kind attention.
Okay, thank you so much, Shuntaro, for your very nice talk. Okay, so some question, comment from audience.
Hello.
Okay.
Yeah, please ask. Yes, yeah, by yourself.
Thank you for that talk. My question is simple. So your regularity result is optimal?
No, well, so even so, the simple for the elliptic problem, it is expected that a solution is in at most C1 alpha, but it is not. This C1 alpha regularity is not proved yet, because our problem becomes not uniformly elliptic in a facet of a solution. So this function, this E star, is a solution to elliptic equations, this elliptic equation. And so C1 alpha regularity will be expectable. But this is not very, this C1 alpha regularity is very hard.
Oh, okay. Thank you.
Other question? Maybe we can ask later informally after stopping the record.
Okay, can I stop recording now?
Yeah, I think so.